My dear students, this particular session again is going to give you some 100 to 120 marks in just 20 to 25 minutes. So be with me till the end because I'll be discussing some almost 25 to 30 concepts of chemistry, which are asked almost every year in your NEET examination, right? In a very precise way. So be with me till the end. This is going to be super beneficial for all of you. First concept, variation of degree of dissociation with volume and pressure. They'll give you the reaction and they'll ask you, is alpha directly proportional to V? Is alpha inversely proportional to P? Is alpha independent of V? Is alpha dependent on P? Something like that. My dear students, you just have to remember two results. What is that? The first result, degree of dissociation alpha is directly proportional to V raised power delta Ng divided by sum of stoichiometric coefficients of gaseous products. Similarly, alpha degree of dissociation is inversely proportional to P raised power delta Ng divided by sum of stoichiometric coefficients of gaseous products. Now try to understand what it means. For example, this is the question, and they've asked us how alpha depends on V and how alpha depends on P. First of all, my dear students, if I calculate delta Ng for the reaction, delta Ng is equal to number of moles of gaseous products, 1 plus 1, 2, minus number of moles of gaseous reactant, that's 1. So delta Ng is 1. If I talk about the sum of stoichiometric coefficients of gaseous products, since it's a gaseous product, it's a gaseous product. Its stoichiometric coefficient is 1, this is also 1. So 1 plus 1 makes it 2. So sum of stoichiometric coefficients of gaseous products is 2, right? Now, alpha is directly proportional to V raised power delta Ng value is 1 divided by sum of stoichiometric coefficients of gaseous product, that is 2. So I would say alpha is directly proportional to square root of volume. This can be directly asked. Similarly, alpha and pressure. Alpha is inversely proportional to pressure raised power delta Ng, that is 1 divided by sum of stoichiometric coefficients of gaseous product, that's 2. So I would say alpha is inversely proportional to square root of pressure. So these sort of questions are frequently asked. Remember the two formulas and you are sorted. My dear students, moving on to the second concept. The questions are frequently asked from limiting reagent. You'll be given the reaction in the balance form. We are starting with 10 moles each of reactants. How can we calculate the moles of product formed? How can we calculate the moles of excessive reagent left? Simple trick. Number of moles of product is equal to stoichiometric coefficient of product divided by stoichiometric coefficient of limiting reagent multiplied by moles of limiting reagent. Number of moles of excessive reagent which react, stoichiometric coefficient of excessive reagent divided by stoichiometric coefficient of limiting reagent multiplied by number of moles of limiting reagent. Let's try to understand what it means. First thing, my dear students, how do we identify which one is the limiting reagent among the two? In order to identify the limiting reagent, divide the given moles by the respective stoichiometric coefficients. 10 by 2 is 5. 10 by 3 is 3.33. This one is getting the lesser value, so it's my limiting reagent. The other one is my excessive reagent. Limiting reagent gets completely consumed in the reaction. So after some time, you'll find 0 moles of limiting reagent. Some moles of C would have got formed, and some moles of excessive reagent would be left in the container. Now, how many moles of C have got formed? How do we check that? In order to calculate number of moles of C formed, it will be equal to stoichiometric coefficient of C divided by stoichiometric coefficient of limiting reagent multiplied by number of moles of limiting reagent. These are the moles of C which are formed. Now, how many moles of excessive reagent would be left? Since I had taken some 10 moles of excessive reagent, minus, how many have reacted? How do we get the moles of excessive reagent reacted? Stoichiometric coefficient of excessive reagent divided by stoichiometric coefficient of limiting reagent multiplied by number of moles of limiting reagent. So solve this and get the moles of excessive reagent left. So simple trick by means of which you can calculate moles of product formed, you can calculate moles of excessive reagent left. Okay. My dear students, a simple question. Calculate the number of waves made by the electron in the nth Bohr's orbit. They'll ask the question. The electron is moving in the second orbit. How many waves will be made by the electron? The electron is moving in the fifth orbit. How many waves will be made by the electron? Remember, the number of waves made by the electron in the nth Bohr's orbit is always equal to n. So if the electron is moving in the second orbit, it's going to make 2 waves. If the electron is moving in the third orbit, it's going to make 3 waves. If the electron is moving in fifth orbit, it's going to make 5 waves. So simple, one result and you're sorted. One more concept. That is about the nodes, right? How do we calculate the total number of nodes? N minus 1. N represents principal quantum number. Nodes are of two types, spherical or radial. Second one is angular. The value of angular nodes is given by the value of L, azimuthal contour number. The value of spherical nodes will be given by the formula N minus L minus 1. Okay. Now, remember, for S subshell, the value of L is 0. For P subshell, value of L is 1. D subshell, the value of L is 2. F subshell, value of L is 3. Now, for example, they're asking me to calculate total number of nodes in case of 3P. First of all, in 3P, what is the value of N? N value is 3. What is the value of L? L for P is 1. So total nodes, N minus 1. 3 minus 1 is 2. Right? Angular nodes is equal to the value of L. L value is 1. Spherical nodes, N minus L minus 1. The value comes out to be 1. Similarly, what is the value of N here? N is 4. For S subshell, the value of L is 0. Right? Now, my dear students, total number of nodes, N minus 1. So 4 minus 1 is 3. Angular nodes, the value of L, that is 0. Spherical nodes, N minus L minus 1. The value comes out to be 3. Right? The value comes out to be 3. I believe I'm clear with this. Similarly, you can give this a try and let me know its answer in the comment section of the video. My dear students, one direct result between molality and molarity, frequently asked. Frequently asked. Remember, molality of the solution, small m represents molality of the solution, is equal to 1000 multiplied by molarity of the solution divided by 1000 multiplied by density of solution minus molarity into molar mass of solute. Right? For example, these sort of questions are frequently asked. Calculate the molarity of a 2 molar NaOH solution, NaOH aqueous solution. Density of solution is also given. You are done, you are sorted. I'll say molarity is equal to 1000 multiplied by molarity is 2 divided by 1000 multiplied by density of solution is 2 minus molarity, that is 2 multiplied by molar mass of solute, molar mass of NaOH, that is 40. Solve this equation, get the molality of the solution. Pretty much simple. The questions are directly asked from this particular result, remember. Okay. Next question. Direct result between molality and mole fraction. Direct result between molality and mole fraction. Remember, molality is equal to mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute, molar mass of solvent. For example, calculate the molality of an aqueous solution. Aqueous solution means solvent uses water, in which mole fraction of solute is 0.1. Mole fraction of solute is 0.1. So I'll say molality is equal to mole fraction of solute, that is 0.1, multiplied by 1000 divided by 1 minus mole fraction of solute, 0.1, into molar mass of solvent. Solvent used is water. Its molar mass is 18. Solve this, get the molality of the solution. Done and dusted. The next one. Stability of oxidation states. Stability of oxidation state. You get the questions. In which of the following lower oxidation state is stable? In which of the following higher oxidation state is stable? Remember, my dear students, if the difference between successive ionization energies, is greater or equal to 16 electron volts, then lower oxidation state is more stable. For example, this is sodium. You have taken 1 electron out of sodium. It is becoming Na positive. And energy required here is called as ionization energy 1. Similarly, from Na positive to Na positive, energy required is ionization energy 2. So IE1, IE2, these are called as successive ionization energies. And let me tell you, the difference in the successive ionization energies here is equal to 42.7 electron volt. The difference in the successive ionization energies here is equal to 42.7 electron volt. I have to check whether lower oxidation state is more stable or higher is more stable. Lower oxidation state is +1. Higher oxidation state is +2. And this is the rule. If the difference in the successive ionization energies is greater or equal to 16 electron volts, lower oxidation state is more stable. That means +1 is more stable than that of +2. Similarly, if the difference in the successive ionization energies is less or equal to 11 electron volts, then higher oxidation state is more stable. Here in this particular case, the difference in the successive ionization energies is equal to 7.4 electron volt. Lower oxidation state is +1 here, higher is +2. So higher would be more stable. Higher would be more stable because it is following this particular category. Concept next. Variation of equilibrium constant with temperature. My dear students, remember one thing. Equilibrium constant of a particular reaction depends only on temperature. Remember it. Equilibrium constant of a particular reaction depends only on temperature. For endothermic reactions, it is directly proportional to temperature. For exothermic reactions, it is inversely proportional to temperature. At the same time, remember one thing. In case of endothermic reactions, on increasing the temperature, forward shift favors. In case of exothermic reactions, on increasing the temperature, backward shift favors, right? And again, these are two important graphs which I would want every one of you to remember. Ln of equilibrium constant versus 1 by T for endothermic, ln of equilibrium constant versus 1 by T for exothermic. These graphs can be directly asked in your exam. Okay? Moving on to the next concept, pH of buffer. How do we calculate pH of acidic buffer and basic buffer? My dear students, you would have heard about Henderson equation. pH of acidic buffer is equal to pKa plus log of concentration of salt divided by concentration of acid. Similarly, in case of basic buffer, pOH is equal to pKb plus log of concentration of salt divided by concentration of base. For example, this is the question. In this container, you've got a weak acid, and this is the salt of the same weak acid, with a strong base. So this particular mixture I'll be calling as buffer. In order to calculate its pH, since it is the acidic buffer, pKa, let me tell you, Ka value for CH3COH is 1.8 into 10 raised power minus 5. And remember, this is the Ka value for acidic acid. Remember, pK, P of this value is always equal to, remember, P of this value is always equal to 4.74. So I'll say it is 4.74 plus log of concentration of salt. How much is concentration of salt? 0.2. Divided by concentration of acid, 0.1. So it's log 2. Log 2 is 0.3. The value comes out to be 5.04. So this is the pH of the final solution. Simple. Again, if you get the basic buffer, you can calculate pOH from this result. And once you get pOH, then you can say pH is equal to 14 minus pOH. One more direct question from this particular result. Moving on to the next concept. Oxidizing power is directly proportional to SRP, standard reduction potential. Reducing power is directly proportional to SOP. Remember two things and you are done. For example, these are the reactions which are given to me. I have to give the order of oxidizing power. My dear students, first of all, these are your SRP values which are given to you. Tell me one thing. Where do you find the SRP value, the maximum? This is minus 2, minus 3, minus 2.1. Maximum SRP is this one. This is the maximum SRP value, minus 2. Right? More the SRP, more the oxidizing power. So I would say oxidizing power of A positive would be maximum, followed by C tri positive, followed by this B. Okay, this is the oxidizing power. Similarly, you can get the question based on reducing power as well. Remember, your reducing power is directly proportional to SOP, standard oxidation potential. Okay, one important question. Remember, there can be a question asked wherein they'll ask you to calculate oxidation potential and reduction potential of the hydrogen electrode. My dear students, two direct results I'm giving you. Oxidation potential of the hydrogen electrode, 0.0591 into pH of solution. Reduction potential of the hydrogen electrode, minus 0.0591 into pH of the solution. And both the results are valid when the partial pressure of hydrogen gas is equal to 1 atm or 1 bar. For example, this is the question. In this question, you are given with the hydrogen electrode. You have to calculate what? Oxidation potential. Oxidation potential of hydrogen electrode. You already know. What is that? That is 0.0591 multiplied by pH of solution. So first of all, I have to calculate pH. How do we calculate pH? P stands for minus log. Minus log of what? H positive concentration. Is H positive concentration given to me? Yes. How much? 0.1. So 10 raised power minus 1. The value comes out to be 1. My dear students, you got the pH. If you got the pH, the answer is going to be 0.0591 multiplied by 1. So this is the oxidation potential which I was supposed to calculate. Okay? I believe I'm clear with everyone. Now, my dear students, I'm moving on to one more concept. If you look at one more concept, this is one more important concept. Calculation of mole fraction. My dear students, calculation of mole fraction of a component in vapor phase. If you look at this particular concept, what is it exactly? You have got a solution. This is the solution of A and B. A as well as B, both are volatile. So you will find vapors of A as well as vapors of B here. You have got a solution of A and B. Here you will find vapors of A as well as vapors of B. Now, how do we calculate mole fraction of A in vapor phase and mole fraction of B in vapor phase? Two direct results. First of all, let me make you understand this concept a bit in detail. This is the solution of A and B. Let the mole fraction of A in the solution is chi A. Mole fraction of B in the solution is chi B. Similarly, mole fraction of A in the vapor phase is chi A dash. Mole fraction of B in the vapor phase is chi B dash. Okay? So mole fraction of A in the vapor phase is equal to P naught A, chi A divided by PS. PS is the total vapor pressure of the solution, which is calculated with the help of this result. Similarly, mole fraction of B in the vapor phase. P naught B, chi B divided by PS, right? I believe this particular concept, these two results you are directly going to remember from now onwards. My dear students, moving on to one more. Remember, this is one very, very, very important concept and simple at the same time. Sometimes they'll give you a question, they'll give you a molecule, they'll ask you whether it's diamagnetic or paramagnetic. Remember, if you have got a molecule containing even number of electrons, you have got a molecule containing even number of electrons, that will be diamagnetic. Molecule having odd number of electrons, that will be paramagnetic. But remember, that molecule which has got total 10 electrons or 16 electrons or 32 electrons, that is going to be paramagnetic. I told you already, even number of electrons is generally diamagnetic, except 10 electron species, 16 electron species, 32 electron species. Odd electron species are paramagnetic. For example, I'm taking N2, I'm taking O2, I'm taking B2, right? I'm taking anything. So N2 is basically a 14 electron species. It has got 14 electrons. O2 has got 16 electron species. B2, 10 electron species, right? All the three are basically even. All the three are even. So they should be diamagnetic. So 14 will be diamagnetic. But in even there are some exceptions. 10 and 16. 10 and 16. This is going to be paramagnetic. Even this is going to be paramagnetic. So this is what you have to remember. All the even, if the electrons are even, if the total electrons are even, it's supposed to be diamagnetic, except when the total electrons are 10, 16 or 32. They are going to be paramagnetic. Moving on to the next one. Entropy versus pressure. Again important. Remember, entropy and pressure, they are inversely proportional. Entropy and pressure, they are inversely proportional. More the pressure, lesser the entropy. This sort of a question is frequently asked. You are given the reaction and you are supposed to check whether entropy is increasing during the reaction or decreasing. Look at the pressure here, 2 atm. Look at the pressure here, 1 atm. During the reaction, the pressure is decreasing. If pressure is decreasing, that means entropy is increasing. So during this process, entropy increases. And when entropy increases, delta S value is taken as positive, right? Again, one important concept which you should know. One more concept. Calculation of degree of dissociation for weak electrolyte. Calculation of degree of dissociation for weak electrolyte. My dear students, remember, degree of dissociation for a weak electrolyte is equal to molar conductance of a weak electrolyte at a given concentration divided by molar conductance of a weak electrolyte at infinite dilution. At infinite dilution. This is the result which you have to remember. Now, if you look at this question, when the concentration of the weak electrolyte is 0.01 molar, at that point of time, molar conductance value, molar conductance when the concentration is 0.01, that's given to me as 3.907. Now, similarly, at infinite dilution, molar conductance is represented by lambda m naught. This value is 390.7. What do I have to calculate? Alpha. I already know the formula. Alpha is equal to molar conductance at a given concentration, which is 3.907, divided by molar conductance at infinite dilution, that is 390.7. The value comes out to be 10 raised per minus 2. So this is alpha. Now they are asking us to calculate pH of the solution as well. Now you know your CH3COH. Your CH3COH, it's a weak electrolyte. How will it undergo dissociation? CH3CO negative plus H positive. Let its concentration is C, 0, 0. This will be C minus C alpha. This will be C alpha. This will be C alpha. So concentration of H positive in the final solution is C into alpha. Now what is the value of C? C value is 0.01. Alpha is 10 raised per minus 2. So C into alpha will come out to be 10 raised per minus 4. So I would say pH will be equal to minus log of H positive concentration. So the value comes out to be 4. So pH of this solution is nothing but 4. I believe this is clear. Okay. So alpha, degree of dissociation of the weak electrolyte, is equal to molar conductance at a given concentration divided by molar conductance at infinite dilution. Remember this as well. Next concept. Calculation of E naught cell. Standard EMF of the cell is nothing but E naught cathode minus E naught anode. E naught cathode represents SRP of cathode. E naught anode represents SRP of anode. SRP of cathode minus SRP of anode. For example, these are the two half cells which are given to me. These are the two electrodes which are given to me. Their SRP values are given. Now tell me one thing. Which one has got more SRP? This has got more SRP. More the SRP, more the tendency to undergo reduction. Reduction takes place at cathode. So this is my cathode, this is my anode. Since I identified my cathode and anode, so E naught cell is equal to E naught cathode, SRP of cathode, minus E naught anode, SRP of anode. The value comes out to be 1 volt. Pretty much simple. E naught cathode minus E naught anode. SRP of cathode minus SRP of anode. Next concept. Calculation of order from half-life. Calculation of order from half-life. Remember, half-life is directly proportional to initial concentration of reactant raised power 1 minus n, where n represents order of the reaction. So you get this equation, T half 1 divided by T of 2 is equal to A1 by A2 raised power 1 minus n. For example, this is the question. You are given the reaction A gives B. We have to calculate order, and this is the table that's given to me. So choose two columns here. For example, I'm choosing column 1, column 2. This I'll be calling as T of 1. This I'm calling as T of 2. This I'm calling as A1. This I'm calling as A2. Now we use the formula. T of 1 divided by T of 2. So 4 divided by 2 is equal to A1 divided by A2. So 50 divided by 100. Raised power 1 minus n. So this value will be 2. This value will be 1 by 2 raised power 1 minus n. So I can say 2 is equal to 2 raised power n minus 1. Or I can say n minus 1 is equal to 1. N minus 1 is equal to 1. So you can say n value is equal to 2. And what is n? N represents the order of the reaction. So I would say the reaction whose data is given to me, the reaction follows the second order kinetics. Again, very important question, right? Very important concept, frequently asked in the examination. Moving on to the next concept, my dear students. Effect of dilution. Effect of dilution. Again, statement-based questions will be asked from this particular concept. Remember, with dilution, molar conductance as well as equivalent conductance increases. With dilution, molar conductance as well as equivalent conductance increases for weak electrolyte as well as strong electrolyte. Molar conductance as well as equivalent conductance increases for weak as well as strong. But the reason is different. In case of weak electrolyte, molar conductance and equivalent conductance increases because ionization increases. In case of strong electrolyte, molar conductance as well as equivalent conductance increases because interionic distance increases and interionic attractions, they decrease. Because of which lambda m, lambda eq increases. But remember, with dilution, kappa, conductivity, that decreases. Reason? Number of ions per unit volume, that decreases. Anything can be asked. Statement-based questions will be asked from this particular slide. Okay? Remember this as well. Moving on to the next concept. Calculation of Gibbs free energy of reaction from Gibbs free energy of formation. Remember that, guys. Gibbs free energy of the reaction is always equal to Gibbs free energy of formation of product minus Gibbs free energy of formation of reactant. A direct result. Gibbs free energy of reaction is always equal to Gibbs free energy of formation of product minus reactant. For example, this is the reaction given. You are given with the Gibbs free energy of formation of reactants and products. You have to calculate Gibbs free energy of reaction. I would say Gibbs free energy of reaction is equal to Gibbs free energy of formation of product. This is product, stoichiometric coefficient 4 multiplied by 300. This is Gibbs free energy of formation of products minus, talk about reactants, 2 multiplied by this, 2 multiplied by this. Similarly, plus this is going to be 3 multiplied by this, 3 multiplied by 200. Solve this and get the answer. You'll be getting Gibbs free energy of the reaction. Okay? And remember one more thing. Gibbs free energy of formation. Gibbs free energy of formation for any element which will be present in its standard state. Gibbs free energy of formation of any element which will be present in its standard state is taken as 0. Moving on to the next concept. Order versus volume of the vessel. Order versus volume of the vessel. For example, look at this question. The reaction is given. They are saying that on doubling the volume of vessel, rate of the reaction becomes half. Calculate order. My dear students, how do we deal with this question? Assume that order of the reaction is equal to n. Assume that order of the reaction is equal to n. First of all, write the rate law. I can say R is equal to K, concentration of reactant raised per order. Right? Concentration means what? Moles by volume. So I can say R is equal to K, it's moles of A divided by total volume. Raised per what? Raised per n. Let this be equation number 1. Now the question says, the rate becomes half. It becomes R by 2. When volume of vessel is doubled. So instead of V, I'm writing 2V. This is going to be raised per n. Equation number 2. So divide the two equations. You'll be getting the value of n. For example, I'm dividing equation 1 with equation 2. If I divide 1 with 2, R and R gets cancelled. The value comes out to be 2 is equal to K and K cancels. Na by V cancelled. It's going to be V raised per, it's going to be 2 raised per n. So when you solve this, n value is equal to 1. So n represents the order of the reaction. I just made two equations, divided them, got the value of n. That's it. Okay. This is one more concept, my dear students. A very, very, very important concept. Remember that. We are given with 3 reactions. E value for 1 and 2 is given. I need to calculate E value for this particular reaction. My dear students, remember, the reaction whose E value is to be calculated. You have to make this reaction from the reactions whose E value is given. For example, this is equation 1, this equation 2, this equation 3. So technically, I have to make third equation from 1 and 2. How do I make third equation from 1 and 2? Pretty much simple. If I add these two reactions, this term gets cancelled. Cu die positive plus 2 electrons gives Cu. So third equation I'm making when I'm adding 1 and 2, right? And whatever operation you do with the reactions, same operation you do with their delta G values. Remember that. So I can say delta G for the third reaction will be equal to delta G for the first reaction plus delta G for the second reaction. Delta G is equal to minus NFE. So I'll say minus N3 FE3 is equal to minus N1 FE1. This will be plus minus N2 FE2. You would have heard this result. Delta G is equal to minus NFE cell. So F everywhere cancels. Multiply throughout with minus sign. So it will be E3 is equal to N1 E1 plus N2 E2 divided by what? Divided by N3. Now N1, N2, N3 are given. N1 is 1, N2 is 1, N3 is 2. This is the value of N1, this is the value of N2, this is the value of N3. N1, N2, N3 is given. E1, E2 is also given in the question. So put the values, get the value of E3. Frequently asked question, guys. Okay. One more important question based on solubility product. I believe all of you would be knowing how do we make the solubility product expression. Let me still show it to you first of all. Let's say you have got a sparingly soluble salt as AXBY. How will it undergo dissociation? It undergoes dissociation as X times AY positive plus Y times BX negative, right? If the solubility of this salt is S, now 1 mole gives X moles, S gives X times S. 1 gives Y, S gives Y times S. So if I want to write the expression for KSP, how do I write the expression for KSP? It's always going to be concentration of A plus Y raised power stoichiometric coefficient X, concentration of B minus X raised power stoichiometric coefficient Y. Now, concentration of A plus Y is equal to XS raised power X. Similarly, concentration of B minus S, it's YS raised power Y. So it's pretty much simple. X raised power X, Y raised power Y, and it's going to be S raised power X plus Y. This is how you write the general expression for KSP. Now look at the question. Mercurous chloride. Mercurous chloride is your Hg2Cl2. Remember it. How it undergoes dissociation? It is a special case. Remember, it undergoes dissociation as Hg2 di positive plus 2 times Cl negative. Okay? Stoichiometric coefficient here 1, here it's 2. So first of all, we have to calculate what? We have to calculate S. So first of all, if I write KSP expression, this is your X, this is Y, right? So it is going to be X raised power X. Or let me write the general expression. KSP is going to be concentration of Hg2 di positive raised power stoichiometric coefficient 1, concentration of Cl negative raised power stoichiometric coefficient 2. Now, if the solubility is S, right, this is going to be S, this will be 2 times S because stoichiometric coefficient is 2. So this is going to be S raised power 1 and similarly 2S raised power 2. The value comes out to be 4S cube. So I got to know KSP is equal to 4S cube. So from here you can calculate S. S will be equal to KSP divided by 4 whole raised power 1 by 3. KSP is given. Divided that with 4 and whole raised power 1 by 3. That will give you the solubility of your mercurous chloride, which I was supposed to calculate. One last concept, my dear students, which I'll be discussing with you. This is again a frequently asked question. My dear students, you have got 1 mole of non-ideal gas. Non-ideal gas means real gas. It is undergoing a change in state. Initial pressure of the gas is 2 atm. Initial volume is 3 liters. Initial temperature is 95 Kelvin. Now, the gas is undergoing a change in state. Final pressure 4 atm, volume 5 liters, temperature 245 Kelvin. Remember, when pressure and volume of the gas both will be changing, the result between delta H and delta U at that point of time will be equal. Delta H is equal to delta U plus it's going to be P2V2 minus P1V1. Delta H is equal to delta U plus P2V2 minus P1V1. Now, in the question, they have already given you the internal energy change, delta U, that's equal to 30, plus, what is P2 into V2? P2 into V2, 5 4s are 20, minus P1 into V1, that is 6. This is coming out to be 44 atm liter. Now, if they ask you to calculate the answer in joules, you know 1 atm liter is nothing but that is 101.3, so the answer is going to be in joules. My dear students, the concepts, simple concepts which I discussed to you, they are frequently asked in your NEET examination, and again in your re-NEET examination this year, these particular concepts will be asked. So have a proper eye on them, right? And the PDF of this session I'll be sharing on my Telegram channel, which is Wassim Bhat Chemistry Official. WASSIM BHAT Chemistry Official is the name of the Telegram channel. Also, I'll be sharing it in my WhatsApp channel as well. The name of the WhatsApp channel is same. WASSIM BHAT Chemistry Official. Perfect. Taking a leave with this. Wishing you all the luck.